Yeah, well, it was a Tuesday morning. There was a wreck on the expressway there near the Civic Center, all through Malfunction Junction and stuff. They're doing major road work. Evidently, it caused somebody to have an accident. So it already was constricted, so we were down to sometimes 1 and sometimes 2 lane. And that's where Red Mountain Expressway comes in, I-20, 59 come in, everything was coming in, and you were down to that. And I sat in that entrance ramp. It was like this probably for half an hour, never, I was inching along, and was there within sight of where I had started 30 minutes later. It was miserable. All right, let's see if now we can do PowerPoint. Okay. What's that? Oh, let me do slideshow. Okay. From current slide. Okay, and then I've got to get out of presenter mode. And then do function F10 second. Yeah. Didn't you say you thought it was superior? It gives me, well, it gives me access to the, boy, why does it reduce the screen so bad? Okay. All right. Yeah, but you see you got that border at the top and the bottom that the whole thing should be lit, but it's on my screen. Can't do anything with it. All right. Last time we started section 1.1, we were classifying differential equations 3 ways. Does anyone remember what they were? Order. Right. Not, yeah. Type. Ordinary as opposed to partial. We're only going to do ordinary.
That's why that one alluded.
Right. And then the other was by linearity. Okay. All right. And we had already talked about some. Okay. So I put my mark on page 4, middle of the page. I don't know if any of you have books yet. Probably not. Yeah. 2 important special cases of, and I think I had written this before, but maybe I should do it again. Here is an nth order, ordinary, so that's your order and your type, differential equation that's linear. Okay. They keep going back to this form they introduced on the previous page that they could say this. Yuck. Yeah. Took away what? Oh. I got rid of it. I was explaining this to Ashley. My Monday, Wednesday, 8 o'clock class, both days, every desk has been taken. The same students haven't been in here both days, but every desk was taken. And one woman who sat right, one of those 2 seats, said you couldn't see past the cart, couldn't see the screen, and there was no really place for her to go. So I said, let me take this out and slide my desk down and teach from here. So I'm going to be sitting more, which I don't like to do, but it will do. And then if we need, some people still can't see, they've got room to put the desk there. So, all right. So what I was trying, I have to do this every time. Where is my cursor? There it is. There. I guess I could have used the pen. All right. Now, this is a flashback from any questions from last time? Okay. They're going to be using this kind of concept.
You may want to scoot down that way. Shadows. Well, whenever you turn face forward, you're blocking the screen.
Well, that's the trouble with the desk here, is that to get the book, the computer, and...
You probably lay the book on this side. It'd probably be
Well, yeah, except I read better from here. Okay, I'm left-handed, so yeah, so get used to it. Okay, f of x, y, y prime, y double prime, dot dot dot, up to y to the the nth derivative of y, okay, equals 0. Okay, that's sort of the generic form for a differential equation. Okay, now it's an ordinary differential equation in that these are derivatives, not partial derivatives. Okay, so that makes it ordinary. We're not getting into partial differential equations. Okay, now what made it? What would be the order of this one? Yeah, it would be the nth order differential equation, and that could be any number you want, first, second, 15th, whatever. So that's the order. Now, when we're talking about linearity, this form here, okay, this is there. Oh, might have to put Mark Cameron here. Okay. All right. All right. So we're still missing Victor, Javon, and Rena.
Probably won't see Rena, but the other two.
Yeah. And I haven't seen Javon since the first day. So, all right. So here is linearity. If this f is linear in everything that has to do with the y's, not just the derivatives, y itself and every derivative of y. Not necessarily x. The function is a function of x. That could have anything. It could be linear, it could be quadratic, it could be cubic, it could be radical, like to the 2/3 power. It could be a sine, it could be a tangent, an exponential, a log, it could be anything. It doesn't have to be linear in x, but it does have to be linear in all of the y's and all the y derivatives, okay? If f is linear in all those, that means it's a linear ordinary differential equation, okay? Now, they also write it this way. And this, I think I wrote it before this way. A n x d to the nth y dx to the nth plus a to the n minus 1 x d to the n minus 1 y to dx to the n minus 1 plus dot dot dot, go all the way down to a sub 1 x dy dx plus a sub 0 x y equal g of x. Okay. Now that's written the other way. If you subtract the g of x into here, then you're in that form. Then you have a 0 at the end. Okay? But written this way, that basically everything here, this is that. This would be the one just before that. Then count on down, this would be the one that's that one. This would be the one that's that one. And your g of x is outside. Bring it in, on this side, and that would be your function of x. Now, if all of these powers are derivatives are to the first power, then you have a linear differential equation. Okay? If they're not, if any one of those is raised to any power other than 1, and that could be a fractional power or a multiple power, okay, then it's no longer a linear differential equation. Okay? Now, notice what we've got here. This is really expanded, in a sense, the complexity. You have coefficients for each of these terms, and those coefficients are actually functions of x. They can't be functions of y, because if this was a function of y, this would not be a linear term, because you'd have a cross product in there, okay? Both depending on y. So all these coefficient functions are functions of x and x alone. And your constant, well, your other function, what it's equal to, is a function of x and x alone. But your y's are all to the first power. So not only are they not to multiple powers, but neither are they multiplied by each other. In other words, you couldn't have a y cubed, y double prime multiplied by y fifth prime in the same term. That would not be linear anymore. So the only place that the y or its derivative will show up is not multiplied by any other y or derivative of y, whether itself or any other. That would be a linear. If they're not linear. Okay. Okay, two important special cases of this one that I've just written here, the second one here, they're calling this is. This is equation 4. This is equation 6. Sorry, I didn't leave room to write it at the end. Are linear first order, that's n equal 1, and linear second order, n equal 2 differential equations. So here would be a linear first order differential equation. A sub 1 of x, that's just a coefficient function, dy dx, plus a sub 0 y, I'm sorry, x. Yuck. This is so used to having a taskbar thing that I can erase, and now I have to, no! Previous. Okay. See, having to hit this button every time. All right. Yeah. Okay. That would be a first order linear ordinary differential equation. There you have every classification. Ordinary, the type. Order, first order. Linear because your y's are all to, there's no y or derivative of y multiplied either by itself or any other power or other term there. The x's, a sub x, this doesn't have to be linear at all. This one doesn't have to be linear at all. That one doesn't have to be linear at all. It's these, the y's. Y's and the derivative of y's are not multiplied by any other y or derivative of y, or even themselves. Okay. That's the ordinary first order differential equation. Here's the second order, a2x d2y dy squared, dx. Yuck! I'm going to have to get a lot more careful about my writing. I get the writing too fast, and then it costs. Look at this. Okay. The x squared plus a 1x dy dx plus a 0x y equal g of x. Okay. That would be an ordinary linear first order differential equation. Okay? Ordinary because there's no partials. Linear because your y's and your derivatives of y's are not multiplied by any other y or derivative of y. And first order, the second order because the maximum derivative is the second derivative. Okay. Got it? Maybe I'm beating dead horses here. Okay. Now, when we go up to this equation again, it's equation 6, we see that the characteristic two properties of linear ordinary differential equations are as follows. Okay? Now, I don't have much room, so what I think I'm going to do is erase these things. That was my first and second order linear ordinary linear differential equations. Okay, because now I want to mention that 6 again, but refer to there. Okay. Two characteristic properties of an linear ordinary differential equation. First, okay, the dependent variable y and all its derivatives, y prime, y double prime, y triple prime, dot, 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 up to y to the nth prime, are of first degree, okay, that is, the power of each term is 1. Okay, now B, or 2. Second, next, okay, the coefficients a sub 0, a sub 1, a sub 2, all the way up to and including a sub n of your y prime, and this is not in the same, yeah, no, they are, okay, y double prime, all the way up to y to the nth prime, depend at most on the individual variable. Depend only on independent variable x. Okay. Now, one thing they've left out here, and that is in those two statements, and I think they mean it to be included here, but the dependent variable y and all of its derivatives are of the first degree. But what they didn't say, neither can any one of them be multiplied by another in the same term. They can be added to each other, but they can't be multiplied. Okay? And neither one of those actually says that, but that's also included there. Wish they had. Now, a nonlinear ordinary differential equation is simply one that is not linear. In other words, one of the y's or y primes is multiplied either by itself, meaning to a power, or is multiplied by another one, so you have a cross product, or is raised to some other power, like the 1/3 power. And they don't really mention that either, except here they say the power of each is term is 1. Oh, and I guess that's how they do it. The power of each term is 1. If you had a y cubed times a y prime, I mean y third derivative times the first derivative, then technically the power of that term would be 2. So we haven't quite defined it that way, but that would be the case. Okay. So I guess they can't get away with their statement there. But they just sort of stuck it in. Okay. Nonlinear functions of the dependent variable or its derivatives, such as sine y or e to the y, cannot, or even e to the y prime, cannot appear in a linear equation. It would be a nonlinear equation. So let's look at example 2. All right. Now let's see. I think what we had to do was first, the last class I did this in didn't allow me to do that, but now we did. Maybe that's, yeah, it would say, it would make me do an unwhite screen, and then the next time I could do a white screen. It was really bizarre.
Maybe if you try to do white screen now, it would mess up.
I don't know. It was strange. But here's example 2. Here's an equation. Y minus x dx plus 4xy dy equals 0. Okay? Here's one. Y double prime minus 2y plus y equals 0. X cubed d3y dx cubed plus x dy dx minus 5y is equal to e to the x. Okay. Now, what's that?
I said I don't see like multiplying the y's together.
Well, I'm a little bit bugged here, and maybe I extended too far here, but it looks like to me that this one has a y and a dy in the same term, and maybe that is allowed, but I didn't think it was. Okay, I think I copied it right. But this is in differential form. Let's just do a little monkeying with that and see if y'all tell me if this is going too far. 4xy dy is equal to, I'm subtracting this term from the other side, right? So I'm going to do it this way. X minus y dx. Yeah, I subtracted it by flipping those two. So that's okay? Okay, now, I'm not dividing by dx, but I'm rewriting it in this form. Okay? All right, now that.
I'm not dividing by dx.
Okay, so that then has us in, now I really didn't have to, I don't guess, subtract like that. I could have just not divided by dx on every term, and that would have given me the same thing. Okay, so let's see what we got. I'll change it back. 4xy dy dx plus y minus x, and you don't really need the parentheses anymore, so let me take those out. This, I think, is okay. This is such a pain to do this every time. Okay, equals 0. Okay, that's the same thing. Okay, now what I can do, I think, is divide every term by y, and that would give me 4x dy dx plus 1 minus, nope. If you do that, now your y is at the minus 1 power, not to the first power. So I tend to say that, I don't know, we'll see. It says are in turn linear first, second, and third order ordinary differential equations. I don't know. If that y wasn't there, I would say without a doubt yes. Is that just being 4x dy? Yeah, no problem there at all. But with a y dy there, I consider that nonlinear. But maybe the book doesn't. They didn't say you couldn't have cross terms, but I was one saying that. Okay, but let's ignore that one. Let's do the next one. Pretty obvious that's a linear equation in your y's. Okay, it's ordinary. It's second order. This is first order, that's for sure. Okay, and this one down here, linear, third order, linear, ordinary differential equation. This over here. That doesn't matter. Oh, that's a function of it. Okay. Now, Okay. Now, actually, they do address something here. They say, we have just demonstrated that the first equation, the one that I was bugging about here, that the first equation is linear in the variable y by writing it in the alternate form. And here's how they wrote it. 4xy prime plus y equal x. Guess what, folks? That's not the same as that if that y is in there. If the y is not in there, that is the same. So yeah, that y is not supposed to be there. It is in the book. They have an error. Okay. That's not supposed to be there. You can't lose it. Okay. That is because what we did here, see, if we lose this y here, then you have 4xy prime plus plus y equals x. Yeah. They miswrote it. Okay, sorry about that. Sorry, I didn't. Yeah. Okay. Now, I had not noticed before that was an error. Okay. I'm going to mark it now so next time I don't go through the same thing again. Okay. Wipe that y out of there. Wash that y right out of my hair. No. Okay. South Pacific. Okay. Let's do it again. And, see?
See.
Unwipe the screen.
What you can do, go down to pointer options. Right, you can see where it says erase all ink on slide.
Yeah. Well, okay. Now wait. Okay. I tried that yesterday. It probably worked today because you were in the room.
No.
That's what happened. And that's exactly what I got last time.
But yeah, it's because you're on a white screen. So unwipe.
Yeah, but the last time I was on a white screen too, getting to this one. I don't know why it worked that time.
Right now, go to pointer options.
Yeah, and now it'll say.
Now see if you can erase all ink on the slide.
Okay, I probably can, but if I went up here, I can go to white screen.
Because you were on a white screen and now you're not, technically.
It's what?
Slide.
Okay, this isn't a white screen here, though?
I mean, it is, but it's not. Because it's a slide. And then the white screen is something you just kind of pull up temporarily in the PowerPoint. But yeah, see if you can erase all the ink on it.
Yeah, I probably can. Okay.
So just instead of doing white screen, just erase all ink on slide.
Okay, but that other one didn't allow me to do it.
Because that was a white screen.
And this isn't?
If you colored this one blue, you'd be able to see the difference.
Okay.
Because
All
this
right.
would be the blue slide, then you pull up the white slide, and you'd have to unwipe the slide and you go back to the blue slide.
I'd say this must be a Microsoft product. Okay, never mind. Okay. All right. Here's some other equations. 1 minus y prime, plus 2y equal e to the x. I do. That is not, and the previous one was not. That's why I had to take out the y to make it not. This is not because this term's no sweat. This term has a cross product. The other one did too, and they just didn't realize it. Okay, this one is fine. That was fine. But this would be a nonlinear because of this right here, and you can't get rid of it and keep this as power as 1. Can't happen. I thought maybe there's some trick. No, there wasn't, because they had it written wrong. Okay. Yeah, because then you would have, it would work in this one, it would work in this one, but then you have e to the x over y. Or e to the x times y to the -1. It's not a power point. That's what I tried to do before, but it didn't work. Then it won't work now. Okay. D2y dx squared plus sine y equals 0. Is that a linear, ordinary differential equation? By the way, second order. Is it? Y would have been fine, sine Y would. Sine X would have been fine, sine Y isn't. Because that's not a linear equation. So that would not be. And how about this one? D fourth Y, dx to the fourth, plus y squared equals 0. No, because this is y squared. X squared, no sweat. Okay? Plus y equal x squared, no sweat. But not y squared. Or y to any power other than 1. Okay. Those are nonlinear first, second, and fourth order differential equations. Make sense? Okay. So let's go back. Type is either ordinary or partial. Okay? One of the, we're going to stick with ordinary in this course. Maybe a few examples of partials, but we'll stick with ordinary. Okay? Linear, order, any order in the world. Some finite order, but yeah, it could be any. But your linearity is either linear or nonlinear. That's all we deal with, linear or nonlinear. So two of them are binary, and the other one is anything. Okay. Now, solutions. Okay. As was stated before, one of the goals of the course is to solve or find solutions of differential equations. This next definition we'll consider the concept of a solution of an ordinary differential equation. Okay? And here's the definition. Now, I could do a white screen, but if I do, I won't be able to do anything else. But if I go to erase all, I will. Okay? Yeah. Because huh?
Because you're on the slide.
Not a screen.
Right. Not a white screen.
Okay. I'm sure it makes sense. Okay.
Because the white screen is like scratch paper.
Right.
And this would be like the actual work or the test or whatever.
Right. Hopefully they're all recording well. Okay. Okay. Now, here's the definition of a solution of an ordinary differential equation. This is definition 1.1.2. Our first definition was what is a differential equation. So here's a solution of an ODE. Solution of an ODE. Ode to math. Okay, no. Ordinary differential equation. Okay. Any function phi defined on that interval I and possessing at least n derivatives, okay, that are continuous on that interval I, okay. Boy, I love these definitions. Which, when they used to have a phrase for this in the Navy. If you can't dazzle them with brilliance, baffle them with BS. Okay, but we won't go into that. So it seems like they're doing some baffling here. Okay, which when submitted, I shouldn't be saying things like that, especially I'm recording them, into an nth order ordinary differential equation. Well, I didn't know, right? ODE. Okay. Reduces the equation to an identity. Okay. Is said to be a solution, bolded that, of the equation on the interval. Okay.
So kind of like simplify it down to an identity. That's basically all this is saying.
What's that?
It's saying you need to simplify it down to an identity.
Exactly.
And it's like 4 words versus
Yeah, right. So any function phi defined on some interval domain and possessing at least n derivatives. You've got to have those n derivatives that are continuous on that thing, because otherwise you can't do an nth degree ordinary differential equation of it. Because if it's not, doesn't have n derivatives that are continuous, you can't do it. Okay, so all that was there. Okay, which when substituted, that function substituted into that nth order ODE, ordinary differential equation, reduces the equation to an identity. Okay, like, well, we'll see an example. That's said to be a solution of that equation on that interval. Okay. In other words, okay, a solution of an nth order ODE, ordinary differential equation, and they go back to that F, capital F, that description of it, okay, is a function phi that possesses at least n derivatives, okay, continuous derivatives, for which that function f of x, phi of x, phi prime of x, dot, 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 all the way up to phi, the nth derivative of phi as a function of x, is equal to 0 for all x on the interval I. Okay? Now, then we say that function phi satisfies or is a solution to the ordinary differential equation that you have at the nth degree ordinary differential equation. Now, notice nothing about linearity is in here, only that it's the order and the the type that is ordinary. Okay, so all right, and like I just said, we say that phi satisfies that ordinary differential equation on the interval I. For our purposes, we shall also assume that the solution phi is a real valued function. We're not going to get into complex valued functions here. Real valued function. In our introductory discussion, we saw that, and this is, I don't know if you remember this, y is equal to e to the 0.1 x squared is a solution to dy dx is equal to 0.2 xy on the interval minus infinity to infinity. In other words, throughout that. Okay? Of course it is. Because when you take the derivative of this, you get e to the 0.1 x squared, which is y, times chain rule 0.2 x. And yeah, that's obviously that. When you're taking the derivative, it makes it obvious. But see, that's what you do. In other words, this is your phi here. We called it y before, you can call it phi now. You can call it anything you want to. Fred, Susan, whatever. But the that is the function. It satisfies that ordinary differential equation, therefore it's a solution.
So, when solving these things, we're going to be looking at the beginning and stuff like on the left, Fred, and then making it into stuff on the right.
We're going to be starting over there and trying to figure out what will make it work. If we did this, we've already done that before. Yeah, that's a piece of cake, okay? Marble cake, it may be hard, but it's still, okay, no problem. All right. Oh, maybe not. Okay. Occasionally, it will be convenient to denote the solution by an alternate symbol, y of x. We just did. They just say y. You could say y of x. You could call it phi or phi of x. It doesn't really matter. Now, the interval of definition, you cannot think solution of an ordinary differential equation without simultaneously thinking interval over which that solution is valid. The interval I in the definition is variously called the interval of definition, interval of existence, interval of validity, domain of the solution, that's what we used to call it, and can be an open interval a to b, a closed interval a to b, or an infinite interval a to infinity, infinity to b, or infinity minus infinity to infinity. Okay. This one happened to be for all numbers. The domain is all the numbers. So let's do example 3. Oops. All right. Example 3. Verify that the indicated function is a solution of the given differential equation on the interval minus infinity to infinity. Here's the differential equation. dy dx is equal to x y to the 1/2. Okay? Here is the equation, or the proposed solution. Y is equal to 1/16 x to the 4th. Now, before we go any further, describe this differential equation.
First order.
First order?
Y is raised to something different than 1.
Okay, so it's nonlinear and it's ordinary. Okay, so.
I always forget about that.
Yeah,
They're all
exactly.
ordinary.
So far they are. Okay? But this is not a linear. And remember, we didn't say anything about linearity here. Not a linear differential equation. But we still say, does this fit the description? Well, let's see if it does. What would you do? This is nice about the car. It had a backing on it. Now I have to hold this in place. Yeah, and then they fall off the desk. Okay. dy dx. Obviously, the people who evaluated this were not mathematicians. And I know what they were. They just talked into the screen. And Screencast-O-Matic does that just as well as Tegrity. Okay? But when you're writing, this is a big difference. Okay. dy dx would be what? Take y and do dy dx. In other words, take the derivative. Yeah. Second. A little louder. 1/4 x to the 3rd. Okay, yes, got it. Okay. Now let's see if this fits that equation. 1/4 x cubed, is that equal to x times what? We got to figure out what y to the 1/2 is. Y to the 1/2 would be what? Which is 1/4 x2. Okay, so x times 1/4 x squared, are those equal? Nope.
Oh, wait, I didn't see the first
X
one.
times, yeah.
Your shadows.
Oh, I see, okay.
Yeah. So
Yeah.
they are the same.
They are the same. So therefore, that's the solution to that differential equation. Okay? Now, I want to say here, but I'm not, Yeah, I will. We're not saying necessarily it's the only solution. This one it probably is, but it is a solution, okay? We may come up with some, we will come up with some, this is a solution, but that's a solution. Maybe something else is a solution. So,
with those, would you look for any of those solutions or all of those solutions?
That's where the problems come, isn't it? Okay. All right, so we verified that. Let's do the B part. In the B part, we will now do pointer options, erase all ink, okay? B part. I far prefer this notation. Y double prime minus 2y prime plus y equals 0. Okay? Now, here is a solution. Are they they're proposing it's a solution. Y is equal to x e to the x. So how are we going to verify that that solution is a solution, that that equation function is a solution for that? Okay, so let's start with y prime. What would y prime be? Guess what we're going to use here? Not chain rule. Not quite power rule. Product rule. Right. Now. Okay. X e to the x, okay, plus e to the x, okay. Then y double prime equal, say again, x e to the x plus e to the x plus e to the x. You got stuck in a groove, aren't you? That's equal to what? Simplify. X e to the x plus 2 e to the x. Okay? Yeah. Now, I have a real I'm real tempted to do this too. That'd be e to the x times x plus 2. Okay? You don't have to do that. But I'm going to see whether it's going to help or not. Okay? I don't think it will. Let's just plug and chug. Okay, this will be x e to the x plus 2 e to the x minus 2 times, and what is your y prime? X e to the x plus e to the x plus, and what's your y? X e to the x. And the question is that equal to 0? Okay? Well, this becomes x e to the x plus 2 e to the x minus 2 x e to the x minus 2 e to the x plus x e to the x equals 0. Is that true? What's that? I know, but I have to. Why is it doing that? Okay. Huh? Okay. Because this is a slide. I didn't intentionally click, but it must have clicked somewhere. Okay. So here's an x e to the x. There's an x e to the x. That's 2 of them. Minus 2 x e to the x. That goes to 0. This is 2e to the x minus 2e to the x. Sure enough, 0 equals 0. There's your identity. Right?
Yeah, I couldn't see half of it until just now.
Oh, I'm sorry. Yeah, this isn't good, is it? Let's try it this way.
See if you can manage that.
Okay. All right. Okay. These two add to 2x e to the x minus 2x e to the x, 2e to the x minus 2e to the x, all those add to 0. So sure enough, that's your we verified that solution, that is a solution to that differential equation. Okay? All right. Now, any questions on that? All right. Now, and by the way, I don't have any time on here, so y'all let me know. 10:30? We got it. 10:45. Yeah, okay, 15 minutes. Note too that in example 3, this was the B part of example 3. Each differential equation possesses the constant solution y is equal to 0 everywhere. A solution of a differential equation that is identically 0 on an interval I is said to be a trivial solution. So what they're saying is, if you put y is equal to 0, and then y prime is equal to 0, y double prime is equal to 0, and you have 0 minus 2 times 0 plus 0 is equal to 0. Yeah, that works. Not a very interesting solution, but it works. And that's called the trivial solution because
It's kind of trivial.
It's pretty trivial. Okay.
The derivative of 0 is still 0?
What's that?
I guess because the derivative of 0 is still 0?
Yeah, that's it.
Double prime is still 0?
All right. All right. Now, let's also talk about a solution curve. The graph of a solution phi of an ordinary differential equation is called a solution curve. Since phi is a differentiable function, it is continuous on the interval I of definition. Okay? Thus, there may be a difference between the graph of a function phi and the graph of a solution phi. What are they saying there? Put another way, the domain of the function phi need not be the same as the interval I of definition or domain of a solution phi. Example 4 illustrates that difference. Aren't these words fun? Okay.
Yeah, sure, it's a lot of them.
Yeah. Here's example 4. The domain of, let me go and go to, all right. Here's a function. Y is equal to 1 over x. Okay? What's the domain of that function?
Anywhere from 1 to -1? No, because it'd be either way.
Second, that's getting better,
Yeah,
but it has nothing to do with 1 and -1.
it'd be infinity to negative.
Oh, is all real numbers, is that what you're saying? Okay, I don't think so.
Oh, because then we could include 0.
You cannot include 0, okay? So your interval of definition here, as they call it, or whatever you want to do, is either got to be all positive x's or all negative x's, but it can't include anything that includes 0. It cannot. Your interval cannot be minus infinity to infinity. It can be minus infinity to 0 open-ended, but not closed-ended. Okay, or negative infinity to -1, or negative 745 to negative 11.3. You know, anything that includes only negatives or only positives, that would be an interval. Okay. Okay. The domain of 1 over x, considered simply as a function, is a set of all real numbers except x equals 0. Now, when we graph it, we plot points on the xy plane. I think you know how this looks, don't you? How would it look, that function? Okay. In the first quadrant, it would look like that. In the fourth quadrant, it would look like that. Okay? Never exists in the third or second because, huh? Yeah, that's exactly how in a purple. Exactly. Okay? Now, I didn't put scales on there, but you know, that's what the function looks like. Not defined at 0, but defined everywhere else. Okay. We plot points in the xy plane corresponding to a judicious sampling of numbers taken from its domain. The rational function y is equal to 1 over x is discontinuous at 0. Its graph in the neighborhood of the origin is given in figure. What's that? Yeah, it is a derivative of natural log of x. Yeah. But that would only be one or the other wings of it. Okay. The function. Okay. The rational function is discontinuous at 0, and its graph in the neighborhood of the origin is given by this figure we just have. The function y is equal to 1 over x is not differentiable at x equals 0, since it's not even defined at x equals 0, so it can't be differentiable there. Since the y-axis, whose equation is x equals 0, is a vertical asymptote of the graph. Okay, blah, blah, blah. Okay. Now, y is equal to 1 over x is also a solution of the linear differential order first order differential equation. Here's the equation. X, y prime plus y is equal to 0. Okay? Now first, that is a ordinary linear first order differential equation. Right. Okay? Now it says y is equal to 1 over x. Is also a solution for that. Okay. Now, it says verify. How would you go about verifying? Okay, yeah. But before I did that, I would rewrite this as x to the minus 1. Now do your y prime, and what would that be? Second? Nope. You're going the other way. Okay. You're integrating it. Okay. Negative 1 x to the negative 2, which now you can go back and write as minus 1 over x squared. Right? Okay, that's your y prime. Now let's plug that in. X times a negative 1 over x squared plus 1 over x, is that equal to 0? What's the first term give you? Second? And what do you get? Negative 1 over x plus 1 over x, sure enough, is equal to 0. So we have verified that solution. That is a solution to that differential equation. Ordinary linear differential equation. Okay? No, I mean, this is okay. Now, so that does satisfy that. Okay? Now, it's a solution to it. Okay? But by saying that, we mean that the function defined on the interval I on which it is differentiable and satisfies the equation. In other words, y is equal to 1 over x is a solution of the differential equation on any interval that does not contain 0. Okay? Like negative 3 to negative 1. Yeah, that's the solution there. But it wouldn't be this, it would be this part. Okay? Or it could be from 1 to 3. Then it would be this part. So you see, it's the same thing there, but it's different parts of that. It cannot be, it'll never be that. It'll either be one side or the other side, or some portion of one side or the other side. But it can't be, it can't cross the 0. Okay? It just can't happen because it's not defined there. That's what they're getting at. Okay? Weird way they said it, but that's what they're getting at. In other words, y is equal to 1 over x is a solution on any interval that does not contain 0. 1/2 to 10, as long as it doesn't contain 0. Negative infinity to 0, not counting 0, parentheses, or 0 to infinity, not counting 0. Can't have a square there, have to have the have to have a parentheses, exactly. All right. All right. Blah, blah, blah. Okay. Now, explicit and implicit solutions. Now, explicit functions, implicit function, when you were in calculus, we talked about this some. Mostly we talked about it in terms of derivatives, implicit derivatives, and but we're talking about functions too. In other words, an explicit function is one you can separate, say y is equal to blah, all in terms of x. But if you can't separate them like that, you can still take derivatives implicitly. I don't know if you remember that, but huh? Okay. Let's see. Okay. A solution in which the dependent variable expressed solely in terms of the independent variable, that's an explicit solution. Okay. For our purposes, we think of the explicit solution as the formula y is equal to phi of x. Phi depends only on x. You could say alpha of x. Why they're using phi's, I don't know. Fine. They like Greek, I guess. Okay. That we can manipulate, evaluate, differentiate, and doing other using just standard rules. Okay? We have just seen that the two examples, y is equal to 1/16. Remember? Yeah. Nope. Y is equal to 1/16 x to the 4th. Okay? And y is equal to x e to the x. Remember those? Y is equal to 1 over x. Those are all y is defined explicitly in terms of x. No y is over there, no x is over here. You can separate them completely. Okay? And you can take derivatives and do whatever you want to those. And then you also had the trivial solution, y is equal to 0. That's an explicit solution of all three equations. That's fine. Okay. When we get down to the business of actually solving some ordinary differential equations, you'll see that the methods of solution do not always lead directly to an explicit solution, y is equal to phi of x. This is particularly true when we attempt to solve nonlinear first-order differential equations. Now, one of those we solved, the one that got this, was a nonlinear, but it still gave you an explicit solution, okay? But not all nonlinears will, okay? Often we'll have to be content with the relation or expression of g of xy is equal to 0. In other words, your solution might also have a y. It has x's, but it could also have y's that you can't separate. Now that's if you had an xy here, that I don't think there's any way to get that out of there. I would say there's no way, but that would be, it could be a solution, but it would be an implicit solution, not explicit. If this had a y up here. And a y out here, yeah, you could divide it out. But up here, I don't think.
To do something with logs or something.
Well, yeah, that's what I was just thinking. If you did that, but then I think you then have y's and log y's. And I don't think you can get those to combine together.
But you can probably get them all on one side.
On one side, yes, but not explicitly. Y is explicitly a function of x. Okay. So here's another definition, 1.1.3. All right. Yuck. Okay. This relation, g of xy equals 0, that we mentioned before, is said to be an implicit solution of an ordinary differential equation ode to math, okay. And that was that ordinary differential equation 4. Remember, that was your F. And remember, the F was also F of X's and Y's, remember? We didn't ever say that. We just said F. Well, it was F of lots of things. X, Y, Y prime, all the way up to Y to the nth. Okay. Now, I don't know if you remember this from before. If you put Y to the nth, that's a power. If you put Y to the nth in parentheses, that's the nth derivative. So you have to sort of do that there. Equals 0. Okay. That equation there. That was what they call ordinary differential equation 4. Okay. On an interval I, okay, provided that there exists, again, these words, there exists okay, at least one function, at least one function phi that satisfies the relation as well as the differential equation on I. Yeah, I was afraid that was happening.
Next class is going to be mad when you know you're late.
I know. All right. All right, we will begin next time at top of page 7. Boy, this is going really slowly. I'll be so glad when y'all get your books. I don't have to write all these things down. So folks listening at home, get your books. Okay. I know. Let's see. All right. And let's see if we've done enough to do any homework exercises. I think so. I'm pretty sure I've got to check and make sure, but I believe, yeah.
We don't have a book.
That's right. But you can, when you get it, you can go back and do it, or you can take some pictures of this if you want to. It's up to you. Any of the odds 1 through 7? Do number 9. Now, just look back there, but you're talking, didn't pick up. Yeah, they have odd number answers in the back. I want to make sure. I have had a few books that did even answers in the back, so I always, yeah. Think you can do either 11 or 13, 15 or 17, and you can look at 19. I don't know for sure. We just introduced the concept, but if you want to stop there, you can. We'll go from there. All right. Let me end this then.